So the next concept that we are going to see is the concept of electric flux. Okay. See, this electric flux has something to speak about the density of field lines. Okay, let's take an example and understand. Let's go with the same positive charge. So due to the positive charge, the electric field is away from it, right? Suppose I take a small area like this. I take my hand itself and this area is taken. If I place it here, right, are you able to see? If I place it here, how many field lines are passing? Two or three, okay, depending on how you are able to perceive it, right? If I move the same thing slightly away, what do you think will happen? So the number of field lines will be lesser. So what is happening? I didn't change the dimension of my hand. I didn't change the dimension of this area. Through the same area, depending on which location you place, you are able to see that the number of field lines through it is changing. Decreasing or increasing, it's changing for sure, right? So if you are able to calculate those number of field lines, that will give you some information related to the electric field intensities, electric field's strength. Meaning, if I take this charge, if I give you another test charge, if you place a test charge here and if you place a test charge here, in which case do you think the force will be more? Obviously, imagine it like a magnet. Okay, I give you a magnet, north pole, south pole. I'll give you another magnetic material. If you bring that magnetic material close to the magnet and you take it slightly away from the magnet, in which scenario will you see that more force is experienced? Obviously near, right? Same logic is applicable here. When you bring the charge here, the distance between them is less, hence it will experience more force. So, is there another way to perceive the same information? This is a known fact. I can say k cube by r square, I will say r, it's inversely proportional and then say the answer. But is there another way to understand the same concept? That's what this electric flux speaks about. It speaks about the density of field lines at a given point. More is the density, means more closer the field lines are, more is going to be the strength of the electric field. So more is the number of field lines. I told you that electric flux, no, it speaks about, it is another name given to the density of field lines. So when I say the density here, it has something to do with the number of field lines. So that's why if you look at the definition, right, it is very clear. The electric flux is defined as the total number of lines of force. Listen to this. Total number of lines of force that are passing through a given area. I would like to add a point to it, perpendicular to it. I'll tell you what is the meaning of this. But are you able to visualize what I'm trying to say? Right? So, if somebody asks you what is electric flux, what is the simple definition of it? Electric flux, what does it speak about? It speaks about the number of field lines that are passing through whom? Passing through a given area, and how are they supposed to get oriented with that area? They should be perpendicular to that area. Okay, let's visualize first, then I'll give you time to copy. Now see, if I take, see, this is there, no? What shape are you able to see approximately? Circle, right? Whereas if I take the same thing and rotate it like this, it will not look like a circle. Meaning, if some portion goes into the plane of the board, some portion comes out of the plane of the board, then it will not be a circle. It will be something like an ellipse. Are you able to understand? So, through this shape, if I say the field lines are oriented in this way, see, this is the shape. Okay, I keep it like this. Let's say the field lines are in this way, where I take the consolidated field strength as E. Okay. Now, what will happen is, what does the definition tell me? It says you count the number of field lines and tell me. But how are those field lines supposed to be oriented? They should not be in some random direction like this. They should be perpendicular to the area itself. Meaning, I should not count these field lines. Rather, I should resolve the field lines into the perpendicular direction and then find it. Okay. So here there is another parameter that comes into picture, which is called as area vector. So whenever you take a shape, for that it has the area is pi r square, but it also has a direction associated, and the direction of area vector is always perpendicular to the surface. Listen to this. Aerial vector is always perpendicular to the surface in outward direction. So it is perpendicular to the surface in the outward direction. Why I use the word outward direction, you will understand when I explain it for a cuboid. Is it clear till this step? Right. So for this shape, what is going to be the direction of aerial vector? It will be towards you. Means if I turn it like this, it will be like this. Am I clear with that? So if I take this to be the area vector, and if I take the angle between them to be theta, then this E can be resolved into two components. What are the two components? One is E cos theta, and the second is going to be E sin theta. E cos theta will be a component in which direction? In the direction perpendicular to the paper. Is it not perpendicular to the surface? It's perpendicular to the surface or parallel to the area vector. Both mean the same. How is it? Perpendicular to the surface or parallel to the area vector. So I need to take this component E cos theta and multiply it with the area, then this is going to give me the flux. So flux is represented by the symbol phi, and if you put a subscript E at the bottom, you call it as electric flux. So electric flux is basically, what is it? It is a product of electric field intensity, area, and cos of the angle between them. Right? So how you can write is electric flux is equal to E vector dot A vector. Am I clear with this? So having said this, there are two things I need to answer. What kind of physical quantity is this? Is this a scalar or a vector quantity? It's a scalar quantity because I'm doing dot product, right? Second, so it's a scalar quantity. Then what about the unit of it? Tejas, listen. Electric field, how is it measured? It's measured in Newton per. I wrote in the previous case, E is equal to F by Q. You remember? So it is measured in Newton per Coulomb, and area is measured in obviously meter square. So the unit of electric flux is going to be Newton meter square per Coulomb. It also has another unit which I'll tell you in the next chapter. So as of now, remember this, Newton meter square per Coulomb. So this is all about electric flux. But one last point I would like to explain. I need to mention why I mentioned this direction. When we solve the problem, we'll understand. So with respect to 2D, when I say outward, either of the side is accepted. But mostly what we'll do is we'll take it in the direction of electric field. Whereas when it comes to 3D, right, you need to be more conscious. Suppose I take this block which is looking the form of a rectangle. Right. So for this rectangular surface, I can define the aerial vector like this. So this is the direction of arrow mark. I can define it like this or like this. Right. I can say this is the direction of area or this is the direction of area, but which one should I consider according to the definition? I should take the rightward one or the leftward one? You should always take the one which is outward. So for 2D it doesn't make any difference. 3D it makes a difference, and when we apply it in the problem, this is the question I'll be stressing upon. Next time I'm not going to do. There are two important questions from your textbook that I'll solve. At that point you should be able to understand. Is this registered? Right? So this is the overall concept related to the electric flux. So please make a note of this.